Hello friends, we have to start new topic, effect of impurities and surface tension. First is effect of impurities. When sparingly soluble substance such as phenol detergent is added to water, surface tension of water decreases. Means when we have to add some impurity like phenol or a detergent in water, then surface tension of water decreases. Second one, when insoluble impurity is added into water, surface tension of water decreases. Means if we have to add insoluble impurity like added into water, surface tension of water decreases. Third one, when soluble substance such as sodium chloride, that is the common salt, is dissolved in water, surface tension of water increases. Next topic, effect of temperature. In most of liquids, as the temperature increases, surface tension decreases. Most of liquids, if we have to increase the temperature, surface tension decreases. The temperature at which surface tension becomes zero, called as a critical temperature of a boiling point, or is called as a critical temperature. Temperature at which surface tension becomes zero. Temperature at which surface tension becomes zero, called as critical temperature. The surface tension of a liquid decreases with increasing temperature of the liquid. For small temperature differences, the decrease in surface tension is nearly directly proportional to the temperature rise. The surface tension of a liquid becomes zero as at its critical temperature. The surface tension increases with increasing temperature only in case of molten copper and molten cadmium. Next topic, shape of a liquid drop on solid surface in terms of interfacial tensions. A liquid surface in general is curved. A liquid surface in general is curved where it meets a solid. The angle between solid surface and the tangent of the liquid or tangent to the liquid surface at the extreme edge of the liquid as measured through the liquid called as angle of contact. Now here figure shows interfacial tensions that act in equilibrium at the common point of a liquid, solid and gas, that is air and vapor. Liquid, solid and here liquid, solid and gas, and therefore T1 is equal to the liquid solid interfacial tension, T2 equal to the solid gas interfacial tension, and T3 the liquid gas interfacial tension. Theta is the angle of contact for the liquid solid pair is the angle between T1 and T3. The equilibrium force equation is T3 cos theta plus T1 minus T2 equal to 0. The equilibrium force equation is T3 cos theta plus T1 minus T2 equal to 0. Then rearranging this equation we get cos theta equal to T2 minus T1 upon T3. Now here case first, if T2 is greater than T1, cos theta is a positive and angle of contact is theta is less than 90 degree, so that liquid wets the surface. Second case, if T2 is less than T1 and that time cos theta is negative and Q is obtuse, so that liquid is non-wetting. Case 3, if T2 minus T1 is approximately equal to T3, cos theta equal to 1 and theta is approximately 0. Case 4, if T2 minus T1 is greater than T3, cos theta will be greater than 1, and which is impossible, so that there will be no equilibrium and the liquid will spread over the solid surface. Next topic is drops and bubbles. Why water and bubbles are drops? Whenever liquid is left to itself, it tends to acquire the least possible surface area, so that it has least surface energy, so it has more stability. And therefore, for more stability, they acquire the shape of a sphere, as sphere has least possible area. Means shape of a sphere is the minimum minimum shape, and therefore liquid drop acquires the spherical in shape. Difference between drop cavity and bubble. Now here drop is a spherical structure filled with water. There is only one interface in the drop. The interface separates water and air. For example, water droplet. Second one is cavity. Cavity is a spherical shape filled with air. In the surroundings there is water, and in middle there is cavity filled with air. There is only one interface which separates air and water. For example, bubble inside the aquarium. Third one is bubble. In a bubble, there are two interfaces. One is air water and another is water and air. Inside a bubble, there is air outside, but it consists of thin film of water. Next topic, Laplace law for a spherical membrane. Consider a spherical drop as shown in the figure. Let Pi be the pressure inside the drop. Here Pi be the pressure inside the drop and Po be the pressure outside it. As the drop is spherical in shape, the pressure Pi inside the drop is greater than P0. Means pressure outside. Therefore, the excess pressure inside the drop is Pi minus P0. Let the radius of drop increase from r to r plus delta r, where delta r is very small, so that the pressure inside the drop remains almost constant. Let the initial surface area of the drop be A1 is equal to 4 pi r square, and the final surface area of drop will be A2 is equal to 4 pi inside bracket r plus delta r square. Therefore, A2 is equal to 4 pi solve this bracket r square plus twice r delta r plus delta r square, and therefore A2 equal to 4 pi r square plus 8 pi r delta r plus 4 pi delta r square. As delta r is very small, delta r square can be neglected, and therefore we have to get A2 equal to 4 pi r square plus 8 pi r delta r. Thus, increase in surface area of the drop is dA equal to A2 minus A1, and that is equal to 4 pi r square plus 8 pi r delta r minus 4 pi r square. Here 4 pi r square gets cancelled. Remaining answer is 8 pi r into delta r. Work done in increasing the surface area by dA is stored as excess surface energy, and therefore dW is equal to TdA. And here dA is nothing but the 8 pi r delta r, and therefore we have to put here dW is equal to T inside bracket 8 pi r delta r. This work done is also equal to the product of the force F, which causes increase in the area of the bubble, and the displacement delta r, which is the increase in radius of the bubble. And therefore dW is equal to F into delta r. The excess force is given by excess pressure into surface area. And therefore F is equal to Pi minus P0 4 pi r square. Equating equation 2 and equation 2 and equation 3, we get T inside bracket 8 pi r delta r equal to Pi minus P0 4 pi r square into delta r, and therefore Pi minus P0 equal to 2T upon r, equation number 5. And this equation gives the excess pressure inside a drop. This is called Laplace law of spherical membrane, or Young Laplace equation in spherical form. Next topic, pressure difference across a curved liquid surface. Every molecule lying within a surface film of static liquid is pulled tangentially by forces due to surface tension. The direction of their resultant, means Fr on a molecule, depends upon the shape of that liquid surface and decides the cohesion pressure at a point just below the liquid surface. There, suppose here consider two molecules, molecule A and molecule B, respectively, just above and below the free surface of the liquid. So the level difference between them is negligibly small and the atmospheric pressure on both is same, P0. Let Fa be the downward force on A and B due to the atmospheric pressure. Here, first point, if the free surface of a liquid is horizontal, the resultant force Fr on molecule B is 0. Then the cohesion pressure is negligible and the net force on A and B is Fa. The pressure difference on the two sides of the liquid surface is 0. Second one, liquid is concave. The resultant force Fr on molecule B outwards away from the liquid opposite to Fa, then the net force on B is less than Fa and the pressure is decreased, and therefore the pressure above the concave liquid or above the concave surface is greater than just below the liquid surface. Liquid is convex. Here liquid is convex. The resultant force on a molecule B acts inwards into the liquid in the direction of Fa. Then the net force on B is greater than Fa and the cohesion pressure is increased. The pressure below the convex liquid surface is greater than just above the liquid surface. Thank you.